Everyone, today we're talking about quality control, also known as QC, and how it is that we calculate it and why we do it. So QC is quality control, and it's measuring the quality of the process that's being done in order to create a laboratory result. Here I have that there are 3 levels of QC. We're mainly talking about the core lab here with an analyzer. This may also be with manual methods. You would have QC with the lab in microbiology, and that would just be making sure that the whole process of plating and incubating is done successfully, and making sure that your organisms are pure organisms, and you're testing that whole process. But we're mainly focusing today on an automated core lab analyzer, just to make it a little more easy to understand. So looking here, you're using QC and you're running it as a normal specimen. But in this case, you would know the quantity of the analytes that you're testing for within the QC. So what is QC? Well, it's usually a liquid reagent or standard that has known quantities of the different analytes that you're looking for. So if you have a CMP, a complete metabolic panel, you would have a QC level 1, level 2, and level 3, all depending on what the manufacturer is. And in each of these, you'd have a level that is either within the low range, the middle range, or the high range of that analyte's normal reference range, or above for the high. Okay, so what you're looking, and below, obviously, for the low. So what we're looking for is to make sure that we're able to identify when a specimen's result is coming in one of those different categories. So on a chemistry analyzer, we would have 3 different bottles, right? And it would contain, each one would contain all the different analytes in a CMP. However, when they're tested, just like when a specimen is tested, the analyzer is going to pull out with the specimen probe out of the QC bottle and put in one cuvette, the QC, whichever level it is, for each analyte. So although we have one QC bottle that we're pulling from, we're going to do a separate cuvette for every single test, because then again, we would have the reagent probe. This was in another video, just to let you know. We'd have the reagent probe come and take out of the reagent bottle. I know these bottles are terrible, whatever. And put into the cuvette as well, stir it, and then we would put it in the incubator and test it. So it's the same testing process that you would use with a specimen. It's just that we are using known quantities. All right. Okay, so now that we know what QC is and why we use it, let's talk about how we actually calculate it. All right, why would we need to know how to calculate it? Well, there is one main reason, and that is because if you have an analyzer whose computer goes down, you may need to calculate it in downtime. And in order to make sure that you're providing specimen results that are accurate, you would need to make sure to know how to do that. So within each level, you're going to be testing for what's called the mean, okay? And then you're also going to be testing for one standard deviation. And then you would also be asked to calculate, oh, this is still level 1, sorry, the 3SD range. Okay, so that's going to be for every single level. You're going to need to know how to do each of these. And in class, what I'm going to do is I'm going to ask you the same thing. Okay, so what does this all mean and how do we do it? How this all comes together is what is called the Levy-Jennings chart. Okay, and what that really is just a plot, a line plot of where the QC actually falls within the acceptable range, and basically plotting out what the acceptable range is. Okay, so the mean is the average. Then we have 1 SD, which is one deviation away from the mean. Then we have 2 SD, which is 2 levels of deviation away from the mean. And then 3 SD, which is 3 levels of deviation away from the mean. So in this type of plot, you can either have it away from the mean in a higher sense or in a lower sense. So the same thing is reflected on the bottom of the chart. Okay, so the main thing that you want to realize is when you're doing QC, you want it to be as close to the mean as possible, because that would be the highest level of accuracy when plotting out the QC. As you can imagine, getting your QC to make it to the mean and that perfect accuracy is very hard to do. So if you're looking at this, there is a bell-shaped curve that ends up being able to be identified here, and essentially all that's saying is that 68%, statistically 68% of QC is going to fall within this 1 SD range here, and 95% is going to fall within the 2 SD range here, and then 99.73% of your QC is going to fall within the 3 SD range. The rest of the statistical analysis would say that you have a little bit, very few that go outside of the 3 SD range, and those would not necessarily be considered accurate. So we do have a set of rules that we follow in order to make sure that what we're reporting out is accurate. So it's the 1 greater than 3 SD and 2 greater than 2 SD rule. Okay, and what that means is I'm okay to accept the QC if within all 3 put together, all 3 levels, there is only one that is greater than or equal to 3 SD, and or there are 2 greater than or equal to 2 SD. So mainly what you're saying is if I have one level of QC that's out in the 3 SD range, so it's sitting outside of the 3 SD range, whether it's on the low or the high side, that is considered out of control QC, and I cannot run specimens at that point. I have to figure out what's going on. Is it a reagent problem? Is it an instrument problem? Did we not calibrate that actual analytes test? You know, we have to figure out what that is. So there is a whole slew of steps that you need to follow in order to make sure that you're bringing QC into control if it was out at some point. Okay, so let's talk about, before we do any plotting or going on about how to put QC back in control, let's talk about how do we calculate it. Okay, so we know that the mean is the average, all right? And so when we give you a question, in the lab, or you're given a QC level, you're going to have a range. All right, so there, for every level, the range basically is provided to you in this type of format. Okay, and so you'll be given a number here. So maybe this number is 5 and this one is 15. And for level 2, the same thing. And maybe for this one, it's 25, and this one, it is 60. And for level 3, X1 and X2. And maybe for this one, it's 80 and 100. Okay, this is just whatever analyte. We're just doing the math for this at the moment. So if we know that that's what a range looks like when we go to calculate it, how do we calculate average? Well, we're going to take X1 plus X2, and since there's 2 of them, we're going to divide them by 2, and that would be the average. So that would be the same on all of these. And that would give us what the line is, that perfect line that we want, what value that is for level 1, level 2, and level 3. And again, they're separate. Remember, they're separate. All right. So then for 1 SD, we're looking at this whole range right here. Okay, we're going from this spot, the 1 SD line on top. Sorry, we're on 2. I apologize. The 2 SD line on top and the 2 SD line on bottom, standard deviation. But notice how many lines are there away from the mean in that range. So we're doing this range right here. How many lines are there? There's 1, 2, 3, 4 within that range away from the mean, right? So knowing that, we want to make sure that we put that into our calculation. So knowing that we have 2 units of data, or 2 pieces of data to identify our range, we know, I forgot to tell you this, but this is the 2 SD range right here. All right, so we are trying to calculate the 1 SD, but we have the 2 SD range available for data points. So that's why we're doing this 2 SD range right here, because these 2 X's are a known value because they're given. So in order to know how to figure out what 1 SD is, we have to mathematically use what we know. And we also are noting that in between each of these little spots, there's 4 spaces in between each of these spots, okay? 2 away from the mean on the upper side and 2 away from the mean on the bottom side, all right? So knowing that, what we can do is we can take X2 minus X1 over 4, because remember, there's 4 spaces. And if we did this the opposite way and we did X1 minus X2, that would take us well below this 3 SD range, and that's why the equation is not that way. All right, so far we have the equation for the mean, we have the equation for 1 SD, and this is all from knowing that 2 SD range. You're always going to be given the 2 SD range, okay? So now we're moving on to the 3 SD range. How do we figure that out? Well, again, we want to go with things that we know. So when we identify what the 1 SD is, we're able to then use that with what we already know and figure out that range. Okay, so what we already know are these 2 numbers, the 2 SD range, right? And now we're going to also know what the space is between each of these lines. So in that case, what we can do in order to figure this range out is we'll do x2 plus 1 SD. That's going to equal the higher side, right? And then we're going to do x1, which is the lower 2 SD range, minus 1 SD. And that's going to equal the low. All right, so that's a range. So if we wanted to write this just in one line, what we could say is 2 SD plus or minus 1 SD, and that's what equals the 3 SD range. Okay, so now we're going to practice that, and then we're going to plot it, and we're going to do it for every single level. We got level 1, level 2, and level 3. All right, so our practice problem here, we'll do level 1 first. So we know that level 1, x1 is 5 and x2 is 15. Okay, so I want to figure out the mean for level 1. So do you remember the equation? It's right up here. It's the average, right? So we want x1 plus x2 divided by 2. So to plug that in, it would be 5 plus 15 divided by 2. And that's 20 divided by 2. And that's going to equal 10. Okay, so our average here, our mean line, is going to be 10. Now we want to do the 1 SD. All right, we're going to figure this one out. So 1 SD equals x2 minus x1 over 4. So again, we're going to plug these in, but in this time, it's going to be switched, right? x2 is first, so 15 minus 5 over 4. And that's going to equal 10 divided by 4, which equals 2.5. All right, now the last one that we're going to do is the 3 SD range, right? And if it's written in a line, it's 2 SD plus or minus 1 SD, okay? But in order to figure out what that actually is, we can break it down into those 2 lines, all right? So the 3 SD range equals x2 plus 1 SD and x1 minus 1 SD. So x2 is 15. And we're going to add the 1 SD to it. So 1 SD is the 2.5. 2.5. And that equals 17.5. All right, let's go down to x1. That would be 5 minus 2.5. And that equals 2.5. Oops. Okay, so let's continue on and do the other levels. All right, I'll do them off camera and then I'll show you. And then what we're going to do is we're going to plot it on the Levy-Jennings chart, and we're going to provide some example runs and decide whether the QC is in or the QC is out. And then after we figure that out, we're going to talk about what do we do. All right, so hold on, I'll be right back. Okay, so here I've gone ahead and done the other 2 levels. There's a lot there. All right, so this is the kind of thing students would be expected to do in class as part of maybe an exam. Okay, so they would be expected to show their work. That way I can figure out where it was that maybe there was a mistake, if there was a mistake, and they can get partial credit and then also learn from what they can see that they did. Okay, so the numbers that we're going to use, I'm going to highlight them so we can see them easily. All right, so here they are. They're all highlighted. And what we're now going to do is plot them onto the Levy-Jennings chart that we have here. So to first make a statement here, there would be a different Levy-Jennings chart for each level, but I have limited room. So we're going to put them on the same one, but plot the levels and separate them by a line. Okay. So for level 1, our mean is 10. Maybe I'll do this in a different color. That might be a better idea. Okay. So the mean for level 1 is 10. And 1 SD is 2.5. Okay, so what we're going to have to do is add 2.5 to 10. All right, so 2.5 would be 12.5, right? And then for 2 SD, we already know that for level 2, it's 15. Okay, so the great way to check your math is to make sure that these work. So if I had 2.5 to 12.5, is that 15? And that way I can find out if I messed up here. That's your first indication that you need to go back to check your work if that doesn't match. Okay. And then for 3 SD, my high level is 17.5. So again, I can go back and check my work there and make sure that my math was correct. And so it is. So the next part is below. All right, so 10 minus 2 SD is 7.5. All right, and then we already know level 1's X1, and that is 5. And yes, that is 2.5 below 7.5. And then our 3 SD range plot is 2.5 down here. And so making sure again that 2.5 is 2.5 from 5, and that's true. Okay, so that's our first level. That's level 1. Okay, level 2 is going to be plotted in the middle so that when we do our run of QC, we can figure out if we have it out or in. So I'm going to plot these off camera, but here they are. And if you're practicing along with me, go ahead and plot them. You can just pause it here. Okay, so now I have plotted all of them. Check your answers to make sure that you got the same thing. Check your lines. All right. You can pause it here to do that. The next thing we're going to do is I'm going to provide you with data points that we're going to say were our results from running QC for each level. And then we're going to decide whether they're in or out, and then decide what to do from there. Okay, so for run 1, what I did was I plotted the QC that we ended up getting from running the QC, and we're going to put whether it's in or out and why, using that 1 greater than 3 SD and 2 greater than 2 SD rule. Okay, so let's go ahead and plot the run on here. My first level of my run was 2. Okay, so let's plot 2. 2 is down here. All right. My second level of QC was 32 in run 1. 32 is here. Okay. And my level 3 was 96. And if we're going to plot that, that is right here. So what we have is the red X's. Okay. So what do we notice here? What rules are we achieving or breaking? Okay, so is this in or is this out? Well, we see one that is greater than 3 SD. Okay, so we can write that here, 1 greater than 3 SD. And then, let's see, did I plot that second one correctly? 32, yeah, okay. So then we have 2 that are greater than 1 SD because they're outside of this middle range right here, right? But neither one of them has gone over the 2 SD mark, okay? So we can say that this run is out because of 1 greater than 3 SD. So we could end up remixing and rerunning just the first level because that was the one that was out. The others are within 2 SD range, so that's awesome. All right, so the next thing we're going to do is remix and rerun the original QC, level 1 QC. Okay, so here are the steps of the first time QC is out, depending on how many levels you have. You, if you have 2, you could check the Levy-Jennings charts from the runs that have been in the system, and you could see whether you should just redo both of them or redo just the one or check on it. But the first thing you always do is remix and rerun the original QC. And the reason for that being is because it could just be that, you know, the QC is getting old. It's down at the lower ends of the bottle at this point. It's concentrating because it's been used so much. You don't know, so you're going to check that. All right, so that's the first thing you do. The second thing you would do is if you made sure that this QC was fine and you remixed and you ran it, the next thing you would do is get a new QC. So run new QC. All right, because evidently it might be a QC problem. You're hoping. Okay, so the thing that you're always trying to do first is you're trying to make sure that your consumables, the easiest things to fix, are the problem. You really don't want it to be an instrument problem because that's going to affect your turnaround time of your different specimen analysis. And you'll have doctors and nurses waiting on results in order to, if it's a nurse, to identify the lab results to the doctor maybe and say, hey, the results are in, it's critical, whatever. And then the doctor would decide what the next mode of care is for that patient. All right. So if the QC was still out after you replaced the QC with new one, then you're going to end up looking at the reagents. So you could replace the reagent and run this QC that you already put on there, okay? So it may be that the same thing that happened to this QC happened to the reagent, all right? Consumables, you know, they degrade over time. If you do replace the reagent because that's the issue, then you need to make sure it's the same lot number as was before. If it's not, then you have to calibrate the test anyway and then run QC. But if it is the same lot, then if the QC comes in here, then you're golden and you can go ahead and start running patient results. If the QC was not in and the reagent was the same lot number, or maybe it wasn't the same lot number, you would replace, recalibrate. So the reason that we say recalibrate is because at some point, if this was not a new platform you're putting on your analyzer, then you have calibrated it before at some time, at some point. So this would be recalibration because you've already calibrated it before with that same lot number. If it was a new lot number, it would just be calibrate, okay? So after I recalibrate, I'm going to run my QC again, and it's this new QC, this good QC. If that is still out, then we know it's an instrument problem, and that's not fun. Okay, so the next thing, you know, you've got this instrument issue, and you don't know what to do. Not really. You're going to be awesome laboratorians and you're going to be like, yay, I know what to do. But if it is an instrument problem, it could be something as simple as the monthly maintenance wasn't done or the weekly maintenance wasn't done. And maybe there's some residue on the sample probe or the reagent probe that somebody just didn't want to take the time to clean off. And so it might be something as simple as that. If it's not something as simple as that, you're going to end up having to, whether it is or it's not, you're going to need to notify the supervisor or the TIC, which is the tech in charge. That's an MLS that is in charge of the section, maybe while the supervisor is out or on break. Okay. So notifying that person to make sure that they know, hey, I'm going to have a little bit of a backup right now on my analyzer. I'm in the middle of maybe having to do some kind of maintenance because the other shift didn't do it, or I didn't realize that was due today or whatever. And if it's something that you can't figure out how to do yourself, you're going to call service. All right, so you're calling the company and you're asking for their help to walk you through troubleshooting this analyzer to make sure that you're getting the QC back in and fixing some problem. It might even be that they can't walk you through it and even go remotely into the instrument's computer and try to fix it. Maybe they have to actually come in and the instrument's down for the rest of your shift. That is not fun. But if it's just for one analyte, you can run the analytes that came in, that the QC came in, and it's fine. But maybe that one special test isn't working right. Or if it really is like a broken probe or something, you should see more than one QC having an issue, one level of QC having issue for one analyte. It would be more than that, most likely. Whatever is affected by that part of the analyzer. Okay, so that was run one. Let's do the next one, and then we'll do one more example.